Hello and welcome to day 17 of learning ML from chatgpt. So let's get started. So yesterday we learned about generative models like GANs, like generative adversarial networks. So we have the key concept was basically it says a generator and discriminator. So basically a game, each one trying to distinguish between the real and the fake data, and by doing that, after many iterations, the GAN model becomes better. So let's see what we've got in store for day 17's lesson. Okay, reinforcing learning basics. Introduction to reinforcement learning, Markov decision processes, basic Q-learning algorithm implementation, implement a simple RL agent to solve a grid world problem. So let's get started. So please give me day 17's lesson. Okay. I think I've had some experience with reinforcement learning before, but this was just with the minimax algorithm, which is commonly used in tic-tac-toe and chess, where you're trying to maximize your score whilst minimizing the opponent's score. Okay, so day 17, reinforcement learning basics. But with chess, in Minimax, you go through every possible combination and try and find the best, maximizing your score whilst minimizing the other person's score. With chess, you can see that there's billions of different combinations, so there's certain optimizers that need to be applied in order to make it computationally efficient. What? I don't know what's happened here. I do not know. Okay, day 17, reinforcement learning basics. Reinforcement learning, RL, is a type of machine learning where an agent learns to take actions in an environment to maximize cumulative rewards. Unlike supervisors, type of where agents learn to take actions in an environment to maximize cumulative rewards. Okay, unlike supervised learning, there is no explicit dataset of input-output pairs. The agent learns from the consequences of his actions. So, for example, in tic-tac-toe, this would be, it does a move, and it goes through all the possible combinations to go from that move, and see whether it can win or loss. Win is 1, draw 0, and -1 is a loss. Okay, oops. Go back up. It's just a bit laggy due to the page size. Okay. Markov decision process. The mathematical framework used for modeling RL problems and MDP consists of states, describes the current situation of the agent in the environment, actions, the set of actions the agent can take, rewards, the feedback or reward the agent receives after taking an action. So this could be you have a positive output. For example, if you would win the tic-tac-toe game. And the state, in the case of tic-tac-toe, would be the current state of the board. Action would be the possible moves it could make from the specific board combination. Transitions, the probability of moving from one state to another after taking an action. Policy, the strategy the agent uses to decide which actions to take based on the current state. So this should be whichever, in the tic-tac-toe situation, whichever strategy has the highest output. Q-learning algorithm, a popular RL algorithm used to find the optimal policy. What was policy again? The strategy. Oh, okay. Find the opposite. Okay, yeah, that's given. It works by updating QI, quality value, for each state action pair, which represents the expected future reward. Quality value. Okay, so assume this is quality value is just the reward, how good it is for each state action pair, which represents the agent follows the policy that selects the action with the highest Q value. Okay, So exploration versus exploitation. Exploration, the agent tries new actions to discover more about the environment. The agent chooses the best known action, which is exploitation, known to maximize the reward based on past experiences. Okay, code example. Basic Q-learning algorithm. In this example, we'll implement a simple Q-learning agent to solve a grid world problem. Yes, so I think in the later lessons I'm going to need to start using PyCharm, as the Google Cloud storage is not very high. I don't think it's very high. It's got a max of, it's definitely got a max of 7 megabytes. Okay, so we're having a grid world. So what is a grid world problem? I'll just say, please explain this code in much more detail. Because in the recent lessons, it hasn't been explaining, it's just been saying what the thing is, giving it a whole block of code, and then the assignment. But the minute yesterday, the thing didn't even finish executing or training the model because it took too long for, so Google Cloud just timed out. Okay, so import numpy as np, import random. NumPy is a library for handling numerical data in Python. It provides support for multi-dimensional arrays and operations. Random is used to introduce randomness, such as selecting random actions in the Q-learning agent. Okay. Oh, so we're making it from scratch. Is it possible to make one using TensorFlow? Or do we have to make it from scratch? Oh, it's still up. Okay. So this is, I think, the bit where the maths gets even more complex. I haven't even finished the high school math stage of school yet. So I mean, it doesn't look too complex, but I'll just learn the high level overview of what it is, and yeah, just go from there. Just wait for this to finish up printing summary. Okay. It's probably in high demand at the minute, so it's currently 7 PM local time for me. Okay, I'm going to stop printing there. Because it is possible to do it with TensorFlow. I'd rather do it with TensorFlow, as it's been made by professional engineers, and yeah, it's just easier to do. Because I'm not sure, due to its memory limit. Absolutely possible. Okay, then let's do that. Tabular Q learning, where you discuss the Q tables used to store values for each state action pair. In this case, you don't typically need TensorFlow because the state and action pairs are small enough to be represented directly in a table. Okay, this is simpler but becomes inefficient when dealing with larger state action spaces, where deep learning might be useful. Deep Q learning, neural network approximation using TensorFlow. For more complex environments with large state action spaces, the Q table becomes impractical because it grows too large. Instead, you can use a neural network to approximate the Q values. Okay, that's pretty cool. So we basically, so at the start we have the Q values, which is the state and action. For example, in tic-tac-toe, we could have the state, and then we can the possible actions, and then we can train a neural network, which we've on the Q value table, which is the state and action pairs, to figure out the other Q values, which are the quality values for each state action. So yeah, that's actually really cool. I like that. Okay, here's a high-level outline of how you can use TensorFlow to implement deep Q learning. Okay, so grid world. Okay, same grid world as before. I don't know what. Please explain to me what a grid world is. Oh, it. I don't know, my computer's so slow a minute. Hopefully OBS hasn't crashed. It's going fine. Grid world is a simple environment commonly used in reinforcement learning to illustrate and test various algorithms. It's a grid-like environment where an agent navigates through cells and squares to reach a goal, usually under certain constraints. Grid, 2D grid where each cell is possible position. Okay. Entity, goal state, bottom. Okay. Agent receives positive reward. So this would be added to assume the quality value. Actions. Okay, that's pretty simple actually. Okay, so we have just the grid world as we had before. Then we have the Q network. But why can't we just use a normal dense layer? Okay, anyway. Init cool self.out x. That's one state, dense two. We're just basically doing it manually here. Self.out action size. Okay, yeah. So it's just a simple network in the form we're making it own class. Then QNet we're using TensorFlow. DQN agent. Okay, so this is the random actions and yeah, just the okay. Wait, was it DQN? Let me see. No, it's not transformers. No, it was MDP. Okay. So then, okay, we'll just gloss over this. Now is network that approximates the Q values instead of using Q table. It takes the input, a state as an input, and outputs Q values for each action. Experience replay. The agent stores past experiences in a buffer and samples from it to train on the network. This helps it from breaking the correlation between consecutive experiences, making the training more stable. Target network. A separate copy of the Q network is used as a target for learning, which is updated less frequently. This stabilizes training. Epsilon greedy exploration. The agent explores by selecting random actions, epsilon, and exploits by selecting the action with the highest Q value. So exploits was the ones it already knew that would have a high Q value, and the explorations would just be the just trying out the possible moves. Training network, the agent trains by sampling a batch of experience from the replay buffer and applying the Q learning update rule using the neural network. Conclusion. You're working with simple environments like 4x4 grid. Traditional Q learning with Q table works well and is straightforward to implement from scratch. For far more complex environments with large state or action spaces, better use the deep Q learning where you approximate the Q values using a neural network with TensorFlow or PyTorch. This allows the agent to generalize better in larger, more complex environments. Yeah. Okay, I'm just going to read over the beginning. So let me just read the starting bit. So modeling the reinforcement learning problems consists of a state, action. Okay, this is just how we like test it. Okay, so it's not actually. So a popular reinforcement learning algorithm is used to find the optimal policy. So policy being strategy the agent used, which like the best actions to take based on the current state. it works by updating Q value, quality value for each state action pair, which represents the expected future reward. Okay, the agent follows the policy that selects the action with the highest Q value. Yeah, okay. What was the first? Yeah, okay. I'm just going to read the where I explain the code. Okay, so libraries, we have grid world. Okay. This section defines the environment where the agent operates, a simple 4x4 grid. Okay, so we're just having size as size, and we're having the grid as just 4x4 grid filled with zeros. And we're having the agent as pos not, so it'll be at the top left, and the goal pos will be bottom right. The init method, yeah, okay, I've got that. Reset, so, okay, pretty simple. Step, if action 0, okay, that's also pretty easy. This section make, okay. 3. Q learning agent. This section implements a Q learning agent which learns how to act in the environment by updating its Q values. Okay, so we have, I do not, what's NV? The environment, okay. Q table 0, so we're just filling with just the 16x16 grid. Anyway, alpha controls how much new information overrides off information during the Q value update. Okay, gamma discount factor controls how much future rewards influence the current Q value. A value close to 1 means that the agent highly values future rewards. Exploration rate, epsilon, determines the agent's likelihood of exploring a random action versus exploiting, which is best known. Okay. So learning rate, we can, well, I suppose ChatGPT has picked out the best ones here, like the industry standards. Because I don't have much experience with, I don't have any experience already with using this Q learning agent. So learning rate, the discount factor, just reread it again. It's a bit like jargony. Future rewards influence. Value close to 1 means that, okay. Yeah, so we are having, yeah. Because we want to value future rewards because like future rewards means it's better and quality value is greater. So yeah, we want it to be a better. Exploration rate, epsilon, determines the agent's likelihood of exploring, choosing a random action versus exploiting. Okay, what are we doing? Epsilon, okay. 10% chance. Okay, so now epsilon, greedy strategy, balances exploration and exploitation. So rand is less than, so we're normally going to do exploitation because it's only going to be that 10% of the time. Yeah, okay. So normally we'll just have the exploitation, which, going back to it before, states that we'll use the previously known high Q value pairs things. Okay. Highest Q value, yeah. If the action, yeah, okay, so update Q table. Self state, action, reward, next state. XY equals state, next X, next Y equals next state, best action equals argmax. So we're just finding the highest Q value in our Q table, which is what we'll do because the probability was 0.99. I'm not sure why it wasn't 1, but our gamma was 0.99. Then self table at XY action plus equals, okay, this is just giving me some complex math. This is like it rewarding it for a higher Q value. Q table is updating use Q, sum of the immediate reward and the maximum future reward. Okay, so gamma was the rule, yeah, so gamma was 0.99, so it ruled it well for the future reward. 0.99, it's almost 1, but still less than the actual future reward. Okay, the old Q value, the Q value is a weighted sum of the new information and old information controlled by alpha. Training the Q-learning agent. Okay, this section trains the agent over multiple episodes. Environment, so we're having a 4x4 grid. Agent is a Q-learning agent. Okay, 10,000. I think in the Python code I'll reduce it down a bit. Okay, and just a minute. Okay, sorry about that. Okay, so training. So 1,000 episodes. We're creating a new state every time. While we're not done, we're going to choose. The agent's going to choose an action. Next state equals step, which is what we declared in our grid world class. Agent.update qtable, which is the function we just saw, and state equals next state. Okay. And then we're going to print the qtable that we saw. So the agent interacts with a 4x4 grid environment, learning to reach the goal at the bottom right. Using Q-learning, the algorithm updates its Q values based on rewards and received